In this video, I'll talk about what it means for a molecule to have a dipole moment, and then I'll walk through a few molecules and determine whether or not these molecules have a dipole moment. So first of all, let's say in your bag of tricks you have a couple of plates that are electrostatically charged, and one is negatively charged, and the other one is positively charged. And you throw in your favorite molecules, a group of the same molecules. Now, if those molecules have some dipole moment, that is, if, let me blow this up, if you have one side being more positive than the other, or one side, specifically one side being more negatively charged than the other, then what's going to happen is the negatively charged side will line up being attracted to the positive side. So I'll draw these really big here. So I'd have a negative side being attracted to the positive side. And it might not be perfectly lined up like that. It might be like this. But you would see that. That is if you have a dipole moment. If, on the other hand, you throw in a molecule like, say, N2, the nitrogen gas molecule, and one of the plates is negatively charged and the other plate is positively charged, well, this molecule, N2, does not have a dipole moment, so these would be kind of scattered all over. They would not line up like we see with molecules that have a dipole moment. Okay, so that's the basics of the molecules having a dipole moment. That is, one side of the molecule being more negatively charged than the other. So let's look at hydrogen fluoride, HF. If you look at the Lewis structure of this, you've got H with a bond to the fluorine atom, and you've got these paired electrons on the fluorine atom, and then what you have then is a vector of the dipole moment. And it looks like this. The arrow points toward the atom that is more electronegative. So this is what you see, and so absolutely this does have a dipole moment. So we'll just answer that. And by the way, every diatomic molecule, that is a molecule that has two atoms, every diatomic molecule that has two atoms that are different, like we have here, will have a dipole moment. On the other hand, if you have a diatomic molecule, two atoms, where the atoms are not different, such as N2 and O2, then these will not have a dipole moment. They will be balanced, same negative charge from the left to the right, if you will, when looking at a Lewis structure. Okay, H2O, water. What do you think? Well, actually, it does have a dipole moment, and that is because its molecular geometry is bent. So I'll just draw that. We've got our oxygen with the lone pairs there, and our hydrogens being bent down by those lone pairs, and that creates, it's actually this bending that creates the dipole moment, because we could draw these, this vector. This vector again means pointing toward the atom or the position in the molecule that is more electronegative. So we're pointing toward oxygen there, and these red lines, they're called vectors. So if you added this one plus this other one, just tip to tip, you would have this resultant vector. By the way, vectors don't always have this plus sign on them. That's specific for chemistry. But if you added these vectors, then you would have this resultant vector like this. And so, yes, we have a dipole moment. So the water molecule does have a dipole moment. Next, Ammonia Nh3. Is it trigonal planar or trigonal pyramidal? Well, let's see what happens. When you draw NH3, ammonia, you have to account for these lone pairs, this lone pair of electrons on nitrogen. And what that does is that pushes the hydrogen atoms down, so it is actually pyramidal. So let's do our best to draw this in 3 dimensions. This H over here is behind. It's kind of behind the screen there, going back. So whereas if it were planar, it would just go like this, right? But it is not planar. So let's just scratch that out. It's not planar. It's trigonal pyramidal. And so this is because of this lone pair here, pushes those hydrogen bonds down. And so this also has a dipole moment because the vectors here would not cancel each other out. In fact, they would ultimately point up. And this would be quite a feat to draw the up vector 3-dimensionally, but you get the idea. It's all ultimately going to be going up that way. So this does have a dipole moment. Dipole M for the cool kids. CO2, carbon dioxide. Is it bent? It is not. And it actually turns out that this can be found experimentally with one of these things, these electrostatically charged plates, and you find out that it looks just like this. There's also the molecular geometry part of it, but if I were to look at, this is a double bond here, if I were to look at the dipole, or the vectors that point toward the more electronegative atoms, we see, let's put these lone pairs here. I better do that. But we see that this is linear, and when you have a linear molecule, specifically if they are the both opposing sides are the same atom as we have here, both oxygen, these vectors are going to cancel each other out, so this does not have a dipole moment for the CO2. And it's actually really cool, I think, that you can work this both theoretically on paper here or on computer screen, but also in the lab, and you can put the molecules in one of these things. For most molecules, of course, the ones that play nice, you can put them in this machine, if you will, between these plates and see if they line up. Now, it's not as easy as I just say. You can't just throw stuff in there and just see it with the naked eye, but with the right equipment, better than I have in my backyard, you can find out whether these molecules have a dipole moment. So that's what it means to have a dipole moment, and there's some examples of those that do and do not have dipole moments. Now, I hope that video was helpful. If it was, please consider liking this or sharing it with a friend.